Hi, I got a question a little while back about the mechanisms behind PCR recovery and oxidative pathways and how those are linked. And this is obviously interesting for a NIRS user because NIRS looks at oxygen supply and demand. And if PCR is related to, or if PCR is dependent on oxygen availability and utilization, then NIRS becomes a good tool to look at not only endurance work, but high intensity work as well. So, and we're going to look at a couple papers that kind of underline this. The first one is by Hassler and Richardson. It's skeletal muscle phosphocreatine recovery in exercise trained humans is dependent on O2 availability. It's right there in the title. PCR recovery is dependent on O2 availability. Makes that link right away. And they have this chart that kind of highlights that, pretty easy to understand, with the white dots being hyperoxic recovery and the black dots being hypoxic recovery. And what you see is if you have the model, kind of the line that they draw through the points, you see that the rate of recovery of the white dots, the hyperoxic dots, are higher than the black dots, the hypoxic. So this increased oxygen, or the decrease of oxygen, has an effect on the rate of PCR recovery. It's very interesting. Now, how exactly does that work at like a fundamental level? And I like this paper by Schulman, the glycogen shunt model. I think it does. It's a pretty good read. It's not too complicated. It's a nice review, and it does at least give us some ideas as to why this might be that way. What Schulman does, he kind of outlines this, the energetics of the glycogen shunt model in 3 steps. And you kind of get this first step is the PCR gets broken down to restore ATP. This happens very quickly, 0 to 15 seconds, 0 to 15 milliseconds. And then you have step 2, you need to kind of recover this PCR that you've broken down, and that's happening through glycogen or glucose breakdown. This is what we would then classically call anaerobic metabolism, right? And then comes step 3, which is the resynthesis of this glycogen broken down. And the model says that the glycolytic intermediates, basically the buffer that you have for these glycolytic products, you don't have enough of that anyways. It's going to happen, breakdown of that's going to happen very quickly. You need to resynthesize that. And that's going to happen through oxidative means. And here the example is lactate oxidation, which kind of fits into Brooks's lactate shuttle model, where you end up producing lactate, it gets shuttled around, and then metabolized again. So those things fit quite nicely together in the paper. It also goes through the link to the lactate shuttle theory. What's interesting here is that these things happen very quickly. So we have the steps happening within kind of this 100 millisecond time frame. So for athletic purposes, it's essentially instantaneous. Now, the second point to make is, if these time frames are so small, is that these steps, step 1, 2, and 3, as Schulman points out in his paper, they're for explanatory purposes. These steps don't happen necessarily in order like that. There's probably a big overlap. They're essentially happening all at the same time, which means that in these 100 millisecond time frame, you're getting this oxidative process to try to help curve the loss of PCR and maintain ATP levels. It's happening all the time, and it's happening right away. So this oxygen being utilized, and therefore oxygen being demanded and having to be supplied, is essentially an instantaneous factor in energetics. You see on NIRS too how quickly it responds if you're using your NIRS device. What we also see is by like a paper by Ryan and McCulley, is that your NIRS signal is highly correlated to these PCR signals that you're taking, which makes sense if your PCR recovery and your PCR supplies are directly linked to oxygen demand and oxygen utilization, which, as pointed out by Hassler and Russ Richardson. So all these things kind of fit together. And the important takeaway, of course, for me, using NIRS, is that this kind of at least gives us some theoretical groundwork as to why a NIRS device would be useful. Well, first of all, why NIRS device so quickly responds to high intensity work, which is supposed to be anaerobic, because it's not anaerobic, it's always aerobic, which is something that George Brooks never fails to mention at every conference I'm at when he talks about, which I agree with, obviously. So you need this oxygen use is always happening. It's always happening right away. That's why NIRS responds so quickly on the onset of exercise. It doesn't just flatline. It happens right away. And also then why NIRS is useful not only for some classical kind of aerobic energetics training, but also for what would have been classically anaerobic training, high intensity training. Your NIRS tool becomes very useful to assess your energetics of those types of exercises as well. I hope that helps at least also give points at some of the mechanisms as to why this would work. And I mean, there's a lot more you can go through here, but I'll leave it at that. Thank you very much for listening. Bye-bye.